everyone, and a very, very warm welcome to the 2023 edition of the VG Kulkarni Memorial Lecture. This is the 22nd edition of our flagship series of annual lectures that we have in the memory of our visionary founder, VG Kulkarni. And we've had a range of excellent talks from eminent speakers that have dealt with various aspects that are important issues in science, technology, education, society, etc. And it's an honor to welcome you all to this event. And as always, it's a very special occasion. But this year, it's a very special occasion in more ways than one. First thing, after 3 years, we are back in person. And those of you who are coming here after a while will probably recognize that this is a shiny new VGK Memorial Auditorium. So in the middle, we've managed to get this place refurbished, and I'm delighted that after this major overhaul, we can use this venue for many of the lectures we hold, including this particular event. Now, we went online because of the COVID pandemic, and while the SARS-CoV-2 virus has gone, I am also reminded that there are other coronaviruses, including the influenza coronavirus, which has given me this thing which I sound like a frog perhaps, but sorry about that. But anyway, I had said in more ways than one. So the second reason why it's really special today is that we are actually doing the VGK Memorial Talk on 4th of September, which happens to be VGK's birthday. So, happy birthday, VGK. I won't try to sing with this. So, happy birthday. And my only wish is that Mrs. Vijaya Kulkarni, who was a very, very strong supporter of the lecture series, she's unfortunately not here with us, but I'm glad to see that the family has come, as always. And welcome, Anita ji. I don't see Kishore as yet here. Hopefully he'll join us in a bit. But it's a pleasure to welcome you here. And thanks for all your support over these years. Okay, so third. So that was the second. Third is, this is the start of what promises to be another fantastic year as HBCSE enters its golden jubilee year. Yes, the seed planted by VGK is 50 years young, and we begin our celebrations with today's VGK Memorial Lecture, and we're going to have a series of wonderful events that will be happening over the year ahead, and it will culminate with the 10th edition of the flagship conference series Epistemic in 2024. So there's going to be a lot of delicious stuff happening in the next year ahead. Please be part of it. So, we are on with HBCSE at 50, and for kicking this off, there is no better person we can think of than our very own beloved and respected Professor Arvind Kumar. AK, thank you so much for accepting to do this. Thank you very much. So, I know you want to listen to AK, not to me, but before that, let me request two of the youngest members of the HBCSE family. Where are you guys? You guys are sitting there. Yes, Vishrut and Nishtha are students who have just joined us, not even a month old, I guess. We would like you to welcome, where are those bouquets? There should be bouquets somewhere. I hope this was planned properly. Okay.
People who are joined, okay, so scholars are still with it.
Very nice, very nice. So we would like to recognize Professor Arvind Kumar. Right. And as a representative of VGK's family, Anita ji. Okay, so before we get AK on stage, I'd also like to alert you to the next thing that's happening, which is going to be a symposium on physics education to be hosted right here in November. And it's timed just right that we can also celebrate the young at 80 AK. So that's the next thing coming up. And as we are now eagerly waiting to listen to Professor Arvind Kumar, let me hand it over to Savita, who will formally introduce the speaker. And I haven't used those mics.
Thank you, Arnav. It's my pleasure to introduce Professor Arvind Kumar, who actually don't require any introduction, but just for the benefit of audience. Arvind Kumar, I have taken a liberty not to listen to you. He told me to keep the introduction short, but it is important that people here, the young who have joined HBCSE recently, should know about HBCSE and what happened in the history of HBCSE. So I'm going to say something in that context. So Professor Arvind Kumar did his PhD in physics at Tata Institute of Fundamental Research in area of particle physics. After his postdoc research at European Organization for Nuclear Research, CERN, Geneva, and Westfield College, University of London, he taught at the University Department of Physics, Mumbai, for more than a decade. He then joined Homiva Center for Science Education and was the center director of HBCSE from 1994 till his retirement in 2008. He played a central role in launching the Science Olympiad program in India, which started in 1998. And just to let people know, as we have the Golden Jubilee year for HBCSE, it is also coinciding with the Silver Jubilee year of the Olympiad program. In fact, Physics Olympiad did complete the 25 years in this academic year. And next year, chemistry will be completing, and next to next year, the Biology Olympiad will complete 25 years. So under his tenure as a center director, HBCSE became the nodal center of the country for the academic Olympiad program in basic sciences, including astronomy. Under his leadership, India organized and successfully hosted international Olympiads in chemistry, which was in year 2001, astronomy, which was in year 2006, and in biology, which was in year 2008. He also has started and initiated another key impact program of HBCSE, which is known as National Initiative on Undergraduate Science, NIUS program of HBCSE. He helped establish a unique doctoral program in science education at HBCSE as part of the graduate studies at TIFR, a deemed university. In 2001, he initiated organization of periodic international conferences, which is known as Epistemic, to be hosted by HBCSE to encourage the growth of science education in the country and enhance professional contact with scholars in the field abroad. Additionally, as part of the center's science dissemination efforts, he guided and co-scripted a comprehensive exhibition on history of science, Science a Human Saga, in 1990s. Now, this exhibition was on display, but now it has been converted into its digital form. His primary research interests have been theoretical physics and physics education. He has several research publications in reputed international and national journals in both these diverse fields. He has also authored and co-authored several curricular, co-curricular, and expository books and material at different educational levels. A notable effort was his designing of a large number of instructive problems in the national physics textbooks at senior secondary level brought out by NCERT in 1990s, which have retained in the successive editions of this book. He is a very passionate teacher, and his teaching has been centered around courses in theoretical physics. But his general education work is wide-ranging, spanning from university, college, and high school, which includes secondary and higher secondary stages of education, of science education. In his 4 decades of teaching physics at graduate and undergraduate level, which includes 15 years of teaching at a weekly study circle for physics undergraduate, he has taught nearly every core course in physics theory and a number of specialized courses like quantum field theory, general relativity, nuclear and particle physics several times. At HBCSE graduate school in science education, he extended his intellectual interests and taught courses on philosophy of science and learning theories over a few years. During his tenure at HBCSE, he chaired or was a member of several apex committees in the country in areas of education and science communication. He was a member of National Steering Committee for National Curriculum Framework 2005, where he chaired the focus group on teaching science set up as a part of this effort. Earlier, he has also participated in designing of UGC curriculum for BSc. He is Fellow of National Academy of Sciences in India, and he is a recipient of several prestigious awards. To name a few, he is a recipient of Indian National Science Academy's INSA Teacher Award in 2014 for college and university education, the Third World Academy of Sciences SWAT's Regional Prize for work in school level, that is in 2009, and Indian Nuclear Society Science Communication Award in 2003. He has also received prestigious Godavari Gaurav Puraskar from Kusumagraj Pratishthan in 2006. In 2010, he was awarded Padma Shri by the Honorable President of India for distinguished service in the field of education. It gives me great pleasure to invite Professor Arvind Kumar to deliver his talk. Thank you.
Thank you. Thank you, Savita and Arnab, for your introduction. I am really honored by this invitation to give the VG Kulkarni Memorial Lecture 2023. So before I begin, I would like to pay my respectful tributes to Professor VG Kulkarni, the founder of Homi Bhabha Center, and all that, he founded the center and worked tirelessly for more than 2 decades for its growth, and much of what you see in this center is basically a result of that effort. So my respectful tributes to him again. I am very glad that the members of Professor VG Kulkarni's family continue to attend this session, so I extend my greetings to them. I would also like to extend my greetings on this the beginning of this Golden Jubilee celebrations. I extend greetings and best wishes, and I hope HBCSE continues to go along its upward path in the future. Now I am actually very excited to give the topic of this lecture, and one of the reasons is that it has been a very exciting fortnight for our country in the applications of modern science. We saw the great accomplishments of our space scientists and technologists. Only a fortnight ago, on the successful landing of Chandrayaan-3 on the moon, and 2 days ago we sent again very successfully a probe to study the sun. And it's not just these 2 projects. There are going to be very exciting mega science projects in India, one of which, as you might know, is the LIGO project, which is going to be, I think, situated in Maharashtra somewhere, Hingoli, Maharashtra, which is a mega basic science project, a part of international effort to detect gravitational waves. So it's an exciting time in our country, as far as modern science and its applications are concerned. And therefore, with all these accomplishments, this topic I think is a very apt topic, because what is it about modern science? What is it about this knowledge system of modern science that results in such fantastic accomplishments? What are the features of this knowledge system which help us arrive at such great achievements of human civilization? So I think it's very important that all of us, and especially the young students, get to know about the features, the distinctive features of modern science. So that's what I thought would be a nice topic, and you have all seen the abstract. I won't repeat it. Let me begin with the introduction. Modern science is a massive global enterprise. Science and technology now permeate every aspect of our life. There are a large number of slides, so I am going to read them out quickly. So what is the nature of modern science? That means, what are its methods of inquiry? What kinds of explanation does it accept or not accept? And what norms and values underlie its practice? Now, there are diverse views on these matters. If you have some familiarity with the discipline of philosophy of science, you would know there are a large number of opinions on this matter. It's a deep subject, but I am not going to go into it. I am going to build a very simple narrative that would not be philosophically rigorous at all, but I believe it should be still educationally useful. We will describe the nature of modern science as viewed by some of its best practitioners, the great scientists who contributed significantly to its advance. I am going to quote a number of them. So, in this lecture, double quotes would indicate very reliable sources, authoritative books and so on. There are a few, 2 or 3 quotes which have been taken from the internet, so I cannot be 100% sure about it. Let's start with the thing. The beginnings of modern science. Modern science emerged, this emergence is attributed to the exposition of the heliocentric model by Copernicus in the 16th century. Now, I must tell you that there are many other, this lecture is not on history, so I am going to take a standard textbook narrative, historical narrative, because my purpose here is to use that narrative as a vehicle to tell you the features of modern science. My purpose is not to talk about history and its various narratives that are coming up nowadays, both by philosophers and historians, science, sociologists of science, etc. So that's not my purpose. So this is a standard narrative, and we begin with Copernicus. Therefore, in the heliocentric arrangement, we find that the world has a wonderful commensurability, and that there is a sure linking together in harmony of the movement and magnitude of the orbital circles, such as cannot be found in another way. It's a flowery language. It actually just means that his model allows him to calculate ratios of distances of planets from the sun. Commensurability means something you can measure, calculate. The order of distances and the order of periods were the same. The farther the planet, the higher is the period. So Copernicus completed his book the year of his death in 1543, and of course it met stiff opposition by the authorities of the time, since it went against their beliefs. We move on to Galileo. Epur si move, this is a, and yet it moves. It's a very famous quote attributed to Galileo. I am sure you must have read it somewhere in some books. There is no written record obviously, because Galileo is said to have whispered it while publicly renouncing the Copernican view at his trial in Rome. Galileo is of course promoting the Copernican view in his whisper. It's symbolic of how in the early modern era in Europe, scientists were made to say things which actually they didn't believe in, yet they held on to their ideas in the private. Anyway, the worldview of the Greek philosopher scientist, he was a great thinker, natural philosopher, and he was a polymath, many things all into one person. It was dominant in Europe for 2000 years, but Galileo overthrew Aristotle in astronomy fundamentally and mechanics, and that is why it's often regarded as the father of modern science. Now we will go to the epistemic features of modern science, and just for clarity, I am going to use this word epistemic a number of times. Epistemic or epistemologically, epistemological, etc. It's a simple compact word for anything related to knowledge, its generation, its methods of generating, its justifying, how you justify knowledge and so on. So it's a nice word, so I'm going to use it very often. It's going to be epistemic features of science and social features of science. That's the way it is. So much of it will be epistemic features and then later social features. The role of mathematics in astronomy had been recognized in all ancient civilizations. Galileo sort of applied it to terrestrial motion, free falls, pendulum motion, etc. Early great scientists, Descartes and Newton, etc., were also great mathematicians. And the scientific revolution in 16th century Europe basically was in astronomy and physics, so mathematics was indispensable in those at that time. Hence these statements that the laws of nature are mathematical. The words by the hand of God and similar words were used by Newton and even sometimes metaphorically even Einstein used them. Suggests their belief that the laws of nature were a manifestation of divinity. So it's God who created these laws, etc. However, importantly, modern science rested on the basic belief that the laws of nature by themselves could be discovered by rational inquiry. You don't need to invoke notions of divinity in the laws. So that was one, you can say, epistemological feature. No supernatural notions in science. It was not easy to displace the supernatural by the physical. Early scientists had to struggle with themselves also. This is Kepler who is saying that. Now Kepler had discovered that the planetary orbits are not circular, elliptical. And elliptical means the velocity of the planet is not uniform. If it's a divine thing, then it has to be perfect, circular with uniform velocity. The moment he saw it was elliptical orbits with varying velocity, he came to the conclusion that no, it's not some supernatural, but must be some substantial, means some material, physical force. He was a key figure in the scientific revolution. He discovered his now famous 3 laws. I will not repeat them. The quote shows how these early scientists struggled to replace the then dominant supernatural explanations by explanations based on physical or material agency. This took some time. It's not that it just comes through in one day. Still, the urge to incorporate the supernatural continued even after the scientific revolution. It came to be regarded outside the domain of natural sciences only after, biological, physical sciences particularly, they were so stupendously successful without these notions that it finally was sort of regarded as not something part of modern science. The scientific revolution reached its climax in the work of Isaac Newton. Newton's Principia, published in 1687, founded modern physics, but it influenced human civilization far beyond physics. Then from then on, science progressed rapidly. There was a chemical revolution by Lavoisier, which eventually replaced alchemy, which was earlier good empirical science. They did produce many good empirical results and chemical apparatus and so on for laboratories, but it was based on some speculative aims. We will not go into that. But the modern chemistry, in the modern sense, arrived with Galileo. It became quantitative and so on. The old phlogiston theory was replaced by a new theory of combustion. Similarly, life sciences, I must say in life sciences, there was nothing immediately radical. I mean, there had been advances going on even before the so-called scientific revolution. Again, this is a common word. Many people say, often do not like to use the word scientific revolution, but as I said, I am going to follow the standard narrative of scientists. So anatomy, even before the scientific revolution, there were development. Later microbiology, with the advent of microscope and so on, and taxonomy and so on. So there were developments going on, but a real conceptual revolution arrived only with the theory of evolution by natural selection, by Darwin. This progress in science rode on the earlier various movements, Renaissance and various other movements. We need not go into them. And Europe, which was sort of in dark ages from after the fall of the Roman Empire, from something like around 500 AD to almost 1200 AD, so almost 17, nothing much was going on there as far as science is concerned. But this happened, and then science lifted Europe. Science plus riding over earlier moments lifted Europe out of its dark ages. Now, after this, I will spend some slides on the epistemic features of science. And the way I am going to do it is not, I list the various features of methodology, but sort of how is science related to various other things. This is how I am going. But first, this important point about laws of nature, how, not why. In the Principia, among many other achievements, Newton proved all the three Kepler's empirical laws. By his universal, it was square law of gravitation. And he also unified terrestrial motion, because he tested the fall of a body on the earth with the fall of the moon. Moon is orbiting, but we can regard it as falling towards the earth. And from that, he had already guessed the inverse square law, which he used to prove mathematically the three Kepler's empirical laws. However, his theory was criticized by the followers of Descartes, the great French philosopher and mathematician, whose discovery of analytical geometry played a key role in the scientific revolution. These followers, the Cartesians, believed in a mechanical universe. See, it almost was like a reaction to the old way of thinking, old Aristotelian metaphysical way of thinking. And so because it was, in any revolution, you just throw away the earlier things. And they wanted everything through mechanical terms. Force has to be explained through pushes and pulls and things like that. And on the other, Newton's theory said that one object acts somewhere distant is a force on the other object due to a distant object, and nothing in between. This looked like magic to to this Cartesian philosophy. They were against it. Newton's response is well known. Thus far I have explained the phenomena of the heavens and of our sea by the force of gravity, but I have not yet assigned a cause to gravity, and I do not feign hypothesis. A very famous line by Newton, I do not feign hypothesis. This line captures the spirit of modern science, which first seeks the answer to how before turning to why. The why is sometimes explained in a higher level. It's not that you can never ask the question why, but you start with how is it working, and then why. But an unexplained why still remains at the end. Thus Newton's inverse square law was much later, 200 or more later, was found to be an approximation to the theory of gravity by Einstein. But nobody can say why Einstein's theory works. Einstein has given how the universe works, not why. In general, we do not know why our most fundamental theories are what they are. Now, two important epistemic features of modern science I want to calculate. This is slightly less well known among students, and that is one of which is teleological reasoning. It is now not accepted in modern science. So what is teleological reasoning? Is one in which a phenomena is explained in terms of the purpose, its purpose, final causality as it is called. Teleological reasoning is so much a part of our daily life that we can forget it's not acceptable in modern science. I started from my home today at 1 o'clock so that I can come to give this lecture at 3:30. So this is teleological. My starting from home, that action is being explained in terms of a purpose, in terms of a later purpose. It's very natural. All the time we are doing this. But look at Aristotle says. It's not acceptable in modern science, but Aristotelian physics was full of teleology. For if a thing undergoes a continuous change towards some end, that last stage is actually that for the sake of which. It's a very clear statement of causality based on teleology. Aristotle had a very formal framework of, a very elaborate framework of causality, one of which was teleological. Aristotle used it in his causal explanations. A stone dropped from a tower falls towards the earth because natural motion tends to take an object to its natural place. So you are explaining the motion of the object by the goal that it is going to achieve, namely getting to its natural place. It's a teleological explanation, not acceptable in physics anymore. The scientific revolution not only changed the method of inquiry, which we are always taught in schools that experiments are central now to that of course is true, but it also changed the nature of explanation. This is less emphasized in our schools. It removed teleology from physics. In modern physics, we explain the motion of an object using the laws of motion and initial condition, not in terms of any purpose, any final goal of the object. Sometimes in physics you might think some laws are teleological, like the action principle, etc. But that is always reducible to a local law. An action principle is a global law that a particle travels in such a manner that at the end of it all action becomes an extremum. So it has teleological feeling, but it is actually not teleological because that is equivalent to a local law, and local laws are not teleological. Teleology still persists in biology. The structure of an organ is so marvelously tuned to its function that it seems natural to think that the organ was designed for that goal, for that purpose. It's very natural. But however, that's why it took such a long time and such a counterintuitive idea that the theory of evolution by Darwin and Wallace in the mid-19th century was, however, not teleological. Species evolved through the blind process of inheritable variations acted upon by natural selection, and it gets accumulated over. Evolution has no purpose. There is no such thing that the species want to improve themselves, nothing like that. There are random variation which get selected, the ones which are adaptive, which is called adaptive selection. With the success of this theory, modern natural sciences do not admit of teleological laws. Not just physics, chemistry of course is very closely related to physics, but even biology. As far as the non-volitional domain, we are not talking of biology of volitional domain. Natural sciences, by at least my definition, are non-volitional sciences where human agency etc. we are not talking about. So biology joined chemistry in a unified view of nature based on physics. This is by the great 20th century physicist Steven Weinberg. So biology now no longer has an independent principle which physics simply cannot accommodate. If it were, then you would not have a modern unified natural science. Another important one is anthropocentric reasoning, which was again very common before modern science, but now has been replaced. Anthropo means human. So human-centric reasoning gives a special, unique status to us humans, and by extension to the planet we inhabit, the Earth. The Copernican revolution displaced the Earth. This is all known now very much. It's just Earth is nothing special about Earth, it's just one planet. It is special in the sense it has conditions in which life, over which life can grow, and that's different. And of course, even solar system is nothing special, it's one among billions of others. Still, humans continue to believe in the privileged status, in the cosmic. The theory of evolution by Darwin and Wallace finally eliminated that view from natural sciences. We are like any other species. We may have certain different properties, very different from others. That's some different matter. The lack of the supernatural, any purpose or special status for us in the laws of the physical universe is best captured by Weinberg. It's a beautiful line. Modern science, I am talking of its laws, not its practice. Practice of course has values and everything associated with human. I am talking of laws. Is impersonal, without room for supernatural intervention. It has no sense of purpose, and it offers no hope for certainty. It's one of the finest lines I have come across about modern science, and I already explained to you, but no hope for certainty means it's all provisional. Modern cannot say, well, this is certainly correct. All scientific knowledge is tentative and provisional. The role of experiment in modern science, I will now be a little fast. Observations and experiments are natural to humans. Early civilization used them to develop technology and medicine and so on. So it is not that first time only the modern scientists did experiment, nothing of the kind. They were there in earlier times. However, the hallmark of modern science is a controlled experiment where you observe nature in artificial conditions, control some variables and test theories or infer new regularities not seen otherwise. So it has a different epistemic role. The experiments have a different epistemic, not that they were not earlier. Further, if two or more theories agree with known data, a critical experiment is devised where the predictions of competing theories are different, that enables you to pick the right theory. Many times it is done in science. If there are two theories, then they give you a certain prediction and then you check out which of the theories is correct. Galileo of course did his early experiments of modern science in inclined planes, and he gave insights on free fall, etc. Some of the very important experiments not so much talked about are the experiments on air pressure in the 17th century, and these led to the rejection of Aristotelian doctrine, nature abhors vacuum. I will not go into detail, but it's a very important thing. There was this Aristotelian hangover for a long time, and he said that for some theoretical metaphysical reasons that, well, there cannot be vacuum. Some of those arguments are now known to be wrong, but anyway, that's a different matter. But these people experimentally prove, no, you can create vacuum. Modern science thus elevated the epistemological role of experiment. They are the final arbiters of it. Now, of course, the connection between theory experiment is not as simple as I am telling. It's a very complicated thing, and experiments are theory laden and so on. So these are philosophical issues. I will not get into them, but as far as I am concerned, they don't undermine the objectivity of science. Also, there is no clear sequence. I don't have to tell you this. Theory sometimes experiments suggest experience, theory can suggest, even technology nowadays can suggest new theories, etc., etc. Now we come to mathematics. How is mathematics related to science? I talked of experiments, now mathematics. The status of mathematics was not clear, very clear. Mathematical physics and mathematics were thought to be somewhat indistinguishable. It took some time to realize that two are fundamentally different disciplines, though undoubtedly they greatly influence each other. Mathematics is a logical structure based on axioms, postulates. It adopts a particular kind of language to express logic. The important point is the axioms and postulates of mathematics are a free choice, constrained by only mutual logical consistency. In a theory of science, the starting concepts are not a free choice. They are constrained by nature. Of course, though not fully. This people call theory under determination. It's not that since they have to agree with experiment, they are unique. It's not, they are under, several theories can give you the same experiment. But still, they are not just anything you like. They are not like any logic axioms. This realization came that mathematics is a different discipline when mathematicians discovered geometries which had nothing to do with the usual geometry we are used to, non-Euclidean geometry, and algebraic systems which are not arithmetic systems, which follow non-commutative laws. They don't follow the laws that we are used to in arithmetic and so on, and still they are important mathematical systems. So these products of pure mathematics started around 19th century or so, and it is around that time that people realize that mathematics is very useful for science, but it's a completely independent discipline. Of course, it's amazingly nobody knows why some of these products of pure mathematics turn out to be useful in physics. Like Riemann geometry in the 1850s, he got some 50 years later was useful to Einstein's general relativity. So that's amazing. This is a nice thing. Mathematics was still confused with mathematical physics, such as it was then mathematical astronomy. The vision of mathematics as an autonomous science had been lost sight of in the blaze of Newton's splendor, and it was not until the youthful Gauss again caught the vision, etc., etc. I won't go into it, but he is basically lamenting the fact that Gauss, he did great pure mathematics, number theory, etc. in the prime, in his early years, but then he turned to physics, astronomy, and this series, the effect of this minor planet series on planetary motion, etc. he was involved in. So this author is feeling, I mean, if he could still go on with pure mathematics, what great things could he have achieved. But as it happened, even Gauss, even in these practical assignments, discovered some great pure mathematics, and that's a different matter. Yeah, so overall science does not have the certitude of mathematics. So that's the relationship, I am talking of the relationship between mathematics. It's obvious now, but it took time to realize. They will be seen, this is Huygens, a great physicist in the generation between Newton and Galileo and Newton. They will be seen demonstrations of those kinds which do not produce as great a certitude as those of geometry, means mathematics, and which even differ much therefrom, since whereas the geometers prove their propositions by fixed and incontestable principle, he means axioms, here the principles are verified by the conclusions to be drawn by them. It's a very good description of science, modern science, made as long ago as more than 300 years ago. Modern science is characterized by its emphasis on approximation, estimate of errors in experiments, etc. This again took time to realize. The early great scientists, including Newton, was not so much careful about error analysis, etc., etc. A mathematical model is always an approximation, and then within a model you usually obtain results which are not exact results, but they are often approximation. Experimental measurements always carry errors, so they are always reported with estimates of. So that's the feature of modern science. Now, in 20th century and beyond, what happened was that the earlier science was based to a large extent on visualizable and intuitive concepts, but this became a casualty from 20th century onwards. Most of the important discoveries of modern science later in the 20th century, particularly in physics, were highly non-intuitive. So they had to be admitted, no matter how non-intuitive it is, because they were experimentally, their consequences were experimental. Of course, biology showed this much great progress that you all know very well. The offshoots of this progress, we are all aware of these various great strides in computers and biotechnologies, etc., etc. Still, even though with all these complexities, the aim of basic science is still to explain nature in terms of a small number of entities. So the parsimony as an epistemic aim continues even now in 20th century modern physics. Here is Einstein. The grand aim of all science is to cover the greatest number of empirical facts by logical deduction from the smallest number of hypotheses or axioms. This is sometimes called reductionism, and it's often very much criticized, but that's the epistemic aim of modern science. Now, does science have anything to do with aesthetics? Yes, in its exploratory phase. Aesthetic judgments based on ideas of harmony, symmetry, unifications are quite common even in contemporary science. They are not accepted per se. This is a feature of modern science. Just because an equation looks beautiful to its creator, it doesn't mean it will get accepted. Dirac, the great physicist, used to have this notion of beauty of equations, etc. But Dirac equation was accepted not because it's beautiful, but because it gave strikingly good experimental results, which could not have been done before that. Some of such ideas can be formulated mathematically and their consequences tested. Sometimes they succeed, sometimes they fail. For example, Einstein's heuristic ideas in many cases, often based on analogies or aesthetic judgments, they led to good theories, experimentally verified results. For example, the idea of light quantum. On the other hand, his aesthetic drive, experiment didn't suggest unification of gravity and electromagnetism, but it was just an aesthetic drive. Since he had unified space and time and matter and inertia and gravity, etc., he went on to do this. He failed because it was perhaps a premature attempt. But still it continues to be a drive even in contemporary particle physics. And it's scoring great successes so far. So, in conclusion, what is different about modern science? To summarize, science is often spoken of as a logical enterprise guided by observations and experiment. That of course is true. If you go to a lay person, a lay educated person, and say, what is science? Oh, it's very logical. You know, in our common language, oh, science is very logical. And of course, they also know it's involved in accurate observations, experiments. That of course is true. But logic is not the prerogative of science. Logic, deductive, inductive, abductive means, you know, inference to the best explanation, is used by all of us in daily life. There is nothing special about science as far as logic, basic logic is concerned, because every one of us has Whether you are a scientist, not a scientist, anything, everybody is logical. Modern science uses no different logic. This is a very important point to science students. I mean, I think sometimes it's not a. Then what way is it different? The key point is logic by alone cannot arrive at conclusions. You have to feed in some concepts, some premises. Then you get conclusions. It is in these premises that modern science differs. It's distinctive in its premises. I told you some teleological premise not allowed, supernatural not allowed, anthropocentric notion not allowed. It is in these things that this. And if you have an aesthetic premise, then it's allowed tentatively, subject to experimental verification. Most importantly, and I think that's the central point of what I want to tell, especially the students, that it's not some particular methodology or concepts. It's not that concept of gravity or concept of relativity, these so very well known concepts of modern physics, modern science. It's not one concept or one methodology that defines modern science. So if you find these concepts somewhere else, it doesn't mean that is modern science. Very important point. Because human beings have been logical, and great minds have always existed, and they can always come up with concepts which sometimes match with the concepts of modern science. The important point is the whole complex, connected complex of epistemic and social practices also that characterize modern science. So, before I'll take another 10 minutes, I'll summarize these and then go to the social aspect. So, summary of epistemic feature: no supernatural notions premises, no teleological and anthropocentric explanation. The central role of experiments in suggesting and verifying concepts and theories, whether intuitive or counterintuitive, whether you can picture them or not, it's allowed. Viewing mathematics as an enormously useful but autonomous discipline, distinctly from science. Emphasis on knowing the order of approximation, estimating errors. This is again very important. Even the early modern scientists were not so much alert to this. And a drive, if there is certain error, the drive of the experimentalist to reduce that error, to make it more and more precise. Aesthetic ideas not accepted per se, but viewed as conjectures subject to experimental verification. And parsimony of basic concepts. Of course, parsimony has led to reductive approach, bulk property explained in terms of entities. And if you take to the, you see, it has so far succeeded, so it has become a kind of epistemic feature, the reductionism. Things which were not understood in reducible in terms of physics started getting one after the other. The concept of valency in chemistry, it was a phenomenological concept. Now we understand in terms of more basic concepts. Gene, which was a phenomenological concept, you start explaining. So these are successes of reductionism, but may not be always true. Nobody can say. So far it has succeeded. Science is a relentless pursuit of knowledge. It continually examines the limitations of its theories. There is another very important attitudinal feature. You never feel that is the end. Oh, this is all over. This is the final word. Nothing like that. It's a path that never ends. All scientific knowledge is provisional. There is never a claim to any finality. And of course, modern science has numerous limitations. So even as we admire science and its accomplishments, we have to note its limitations. It's phenomenally successful for simple and moderately complex systems of physical sciences. So physics particularly, it's phenomenally successful because the systems are simple. A hydrogen atom, the energy level of hydrogen atom, it's a simple system. So modern physics is astonishingly successful. You can explain the magnetic moment of electrons to some 8 places of decimal and so on. But you can't have that kind of predictability for complex systems of nature. So, but its explanatory power is less spectacular for complex systems. Though it is growing with computational power, you are still doing now, very large scale astronomical problems, the galaxy formation problems, etc. Now people are doing better, not that they have solved it, but they are doing better with more and more computing power and of course progress in theoretical ideas. Still, it cannot yet handle. This seems to be right now a wall about which there is much debate and nobody knows what it is. The deep issues of consciousness and free will. There is a lot of debate. I'm not going to go into it at all. But so we should also note the limitations, even as we admire its progress. Science and technology, everybody knows. I'll just rapidly read this slide. It has been benign for early modern science. It has cured diseases and reduced drudgery of work, etc., etc. And we just saw its success in humanity's fight against COVID-19. But 20th century technology also brought up very harmful use of science, basically technology, very unwise use, environmental damage, climate change, and potential for destruction on a colossal scale. What's the way out? The way out of this only, I can't think of anything except that people have to come together and use science and technology, not abandon science, but use science and technology with wisdom. And here science alone cannot help you. Science plus socio-cultural interventions can help you this. So now 2-3 slides on the social features and I will stop. Science emerged in a new social environment. So I was so far talking of its knowledge features. It does this, it accepts, it is experiment oriented, etc., etc. But these things don't happen among individuals. They need a socio-cultural ambience for doing that. So it would be wrong to think modern science arose primarily due to a bunch of great scientists in different fields. They of course did significant work, but that's not all. Because outstanding figures exist in every field. It's not just that Newton and Galileo and Einstein are the only great minds in human science. Not at all. There were great minds always in civilizations, everywhere, in all ages. There have been great minds. But they alone are not sufficient for the great leaps in human history. The role of the society is just as vital. Modern science emerged in a certain social setting. We need not go into its details, and it's not even clearly understood how it all happened. There are any number of books on these matters. But there is no doubt that the intellectual and cultural environment in Europe was changing quite dramatically in the late Middle Ages. The new environment called the Age of Reason dawned around the 18th century. Those earlier movements and then success of modern science, it brought in the environment, so-called Enlightenment values, the values of liberty, fraternity, etc. Of course, it's very ironical that Europe brazenly violated all these values. They called themselves to be an era of enlightenment, and yet they did these violations of these values in their colonial drives. But in the post-colonial era, I think at least there is an attempt all over the world to go by these values. Now the socio-cultural norms of science. Scientific community is like any other social community, and therefore it has its own institutions, universities, research institutes, academies, and they have some unwritten norms of practice. These are common ownership. Scientific knowledge, unlike technology, is free for everyone. Nobody has a patent for any law. The concerned scientist, all that he gets is recognition for being the first to discover. And sometimes it leads to priority disputes. Peer review. Every new idea in science is peer reviewed by anonymous referees, no matter how, yes, how eminent you are because of your early great work. It doesn't matter. If you submit a fresh paper, it's going to be reviewed. Consensus. There is no single person, group or institution that decides on the validity of it. It's not that MIT or Harvard decide whether a theory is correct or not. No, it's a whole pool of scientists, reviewers, and all, they criticize, and through this organized skepticism, as a sociologist called it, the pool of widely accepted scientific knowledge emerges. Of course, these norms are based on certain values. Personal values include patience, diligence, cooperative spirit, which is now increasingly most important because the scientific projects are now very collaborative, and most importantly, intellectual honesty, because if your data or if your results, if you are putting out, if they are not correct, then the whole enterprise gets gets a step back. So that value is very important. The most significant social marker of science is that its discourse is free and frank and cordial, where disagreement is not equated to disrespect. Skepticism is valued, and there is no overseeing body to govern interests. So if you have an international conference on something, it's very possible that there will be competing thoughts and people will be arguing against each other very strongly in the conference hall. But when they come out for tea, it's not that they're very cordial. They'll be friendly outside. So disagreement, intellectual disagreement, is not equated to disrespect and things like that. And in fact, it is valued. The more alternative theories are proposed, it's valued. Another vital social marker is the irrelevance of identity labels. Race, gender, religion, class, language, etc. It doesn't matter who is proposing an idea. Ideally speaking, these values were not always there in the early modern science, but they are in 20th, 21st century. The aberrations of these values are getting much reduced. Still, they are not completely out, but they are being mitigated. So it doesn't matter who, from where the person is, it's what the idea is, that is discussed. So when these these values pervade across the world, modern science will be a truly great international enterprise. So at the end now, the last slide will be some concluding remarks. Now I have spoken very admiringly about modern science, and sometimes it gives rise to a feeling that, well, science is everything, modern science, everything. So I want to clarify, the purpose of this talk was to characterize what modern science is. It was not to make judgments or anything else. It was to characterize modern science in terms of its basic features as a cognitive and social endeavor. So if you want to call a product as belonging to modern science, it's likely to be have these features. But my aim was not to privilege natural sciences over other great intellectual and cultural endeavors. There are all kinds of endeavors. Natural sciences is one very important endeavors. But there are endeavors, arts, music, humanities, even spiritual pursuits. Humans respond to nature in different ways, and modern science is one way of responding to nature to understand the physical universe. We talked of the great progress of modern science and the phenomenal success of the mathematical theories of physics. However, for a balanced perspective, here are the last quotes. So I'll end with these last quotes. One thing I have learned in a long life, Albert Einstein is saying that, one thing I have learned in a long life, that all our science measured against reality is primitive and childlike. and yet it's the most precious thing we have. A little more interesting quote is, physics is mathematical not because we know so much about the physical world, but because we know so little. It's only its mathematical properties that we can discover. So I leave the interpretation to you, but it seems to me in Russell saying that nature is very complex, it has various other aspects. It's the mathematical or the measurable, you can say, aspects that science can discover, but that doesn't mean you have exhausted the reality of nature. That is his view. It's for everyone to formulate their view. Okay, that was the end. I just acknowledge some of these slides overlap with my earlier talks, and this epistemic features that I talked about, they appear in a joint paper with Mashood and Majumdar. It was just published last month. And I thank colleagues from HBCSE as well as many friends for many discussions that helped me shape these ideas. These are the references that I quoted, Most of them are very reliable from books, and one or two Galileo quotes are from internet. There are different narratives of historical narratives. That was not my purpose, but if you are interested in alternative narratives about science, of course, this is a famous book by very great scholars on the history of science in India. It's another very good book on history of mathematics. There is this book, very famous historian of science, who basically counters the idea that there was anything very abrupt. I think the idea is that it was a continuity rather than an abrupt break or something like that. It's an interesting recent book which has given a very different perspective to the whole of history of science. I mean, it's a very interesting book which is decidedly against the Eurocentric view. So you can have a look at it. So, and some nice book on evolution, and some of these problems of consciousness, etc., which I did not discuss and about which I don't know much. These are just references. And this, if you want a very quick review, I mean, many of us at HBCSE contributed to the History of Science exhibition which was mentioned. So it will give you it's nowhere comparable to these great scholarly books earlier, but it will give you a good overview of science from the beginning to the 20th century. So that is all I have to say. Thank you.
Okay, thank you very much, Professor Arvind Kumar. So the talk is open for some questions from audience. We'll just take in-person audience question. Yes.
Thank you, sir, for such a lovely enlightening talk. I had a curious question. Sometimes in a scientific study, some scientists may take a leap of faith, like when they are studying something and things are not making sense. It could be like tectonic plates moving or vaccination. At that time when these things were being studied, it was not backed very well by the scientific literature then. So exploring such era where leap of faith is required, will that be also part of modern science, or it should strictly be whatever is known and what's the best direction the foundation allows? You're talking exploring some technology? I did not get it. Exploring
So where
Applied
would
science, yeah.
So where would leap of faith fit
Uh-huh.
in the nature of modern science?
No, faith is.
No, not faith.
I
Like
mean,
some wild guess sometimes scientists make
some
instead.
claims. If the scientist is saying that it is a conjecture and I am going to try it, then there is nothing wrong. But without verification, if the claim is that no, this is the right thing, then of course it's not scientific. Yeah, that's what I said. A conjecture. Heuristic is always there in science. How do you go further in science? You have to.
So can
you
one
have to
start
try.
with it?
I won't.
Maybe?
Yeah.
Is it?
Yeah.
Can one start with that and
Yeah.
maybe build on it or something?
Yeah.
Okay.
Well, I will not congratulate you for this talk. It was wonderful as everybody expected. But I found it a bit surprising that you did not mention falsifiability at all as a feature of science.
Yeah.
So, would you comment on that?
See, what happens is, I mean, it's a very popular thing among scientists, especially falsifiability criteria that Ananda Gupta is talking about, is the criteria advocated by Popper, a great philosopher of science. And the whole idea was to distinguish science from pseudoscience. So science is something in which you stick your neck out, as he said, a good science, and give a clear-cut prediction. If it is correct, then your theory is not falsified. He didn't say theory is correct or confirmed. No, theory is not yet falsified. And if it is wrong, of course. However, what has happened in modern science, this criteria is not always employed. It's a very good criteria, but it's not always employed. So, and it is fairly strongly opposed by philosophers of science for various reasons. First of all, when you say you are falsifying, are you falsifying the whole theory? Are you falsifying? Can you falsify each and every concept of the theory, etc.? There are some deep issues about it, and therefore, although Popper is a scientist philosopher, he is not the philosopher of modern philosophers of science. So I just wanted to avoid that, and I've been saying it is experimentally verified. See, falsification criteria is nothing is confirmed. Things are either falsified or not falsified. That's a bit too much, science in practice doesn't follow this. We say the standard model is reasonably well verified. To say it has not yet been falsified, yes, you can see that, but now what part of the standard model? Standard model gives you certain predictions. Has every bit of the standard model, has it been verified, etc. There are some issues like this, so I didn't want to comment.
So one question, and then we have one online question. So, any one last question from audience? There were a few hands up initially. I missed it. Okay, let's take online question then by this time.
Okay, so this question is from Rohini Godbole. Rohini asks, while ideally we would like science to be truly objective and independent of the attributes such as the nationality, gender, etc. of scientists, there are very stark examples like the work of great Chandrasekhar on his famous limit, which indeed took much longer than it should have to be accepted because it was not acceptable in the citadels of science at that time. What can scientists do that the effect of such impacts of attributes of a person on the development of science is mitigated?
No, I already agreed in the last point that these are the values. See, one is values, the other thing is the departure from these values. These are the values of modern science, and they are being increasingly, modern science is increasingly going along those values. Of course, the time that Dr. Rohini Godbole is mentioning, of course, was not the time. It was at that time racism from science had not yet gone completely. It's probably not gone even now, but everybody will agree it's much less than what it was before. So it's a progress along those values. And what can you do about it? I mean, scientists, especially the great leaders of science, should promote these values, in a very positive way.
So what you're saying is values are the ideals to which
Yeah. Values are, values are always ideals which, and there are delinquencies, even the norms that I told you, the norms, social norms of science are something. There are people who don't follow those norms. So any social enterprise has certain values, and there are delinquencies about it. And what is regarded as a very big delinquency and what is a minor thing, even that we have. Social life also, some things are regarded as minor deviations, some are major. Same thing in science. So whenever there is a collection of human beings, it cannot follow a certain given norms perfectly. The point is the direction of progress. Are we going down or are we going that? As far as I think about basic science, I'm not talking of anything, about the enterprises of basic science currently, from what one reads in good international magazines, I think these values, there is a progress towards mitigation of those aberrations of those values. That's all I would say. Yeah.
Thank you. So we'll take one last question from KS. Yes.
Thank you. Thank you, AK, for the nice talk. So my question is about textbooks in school and the role of history in those textbooks. And a good comparison is with mathematics. In mathematics, history does appear in school textbooks, Pythagoras theorem, Euclid, and so on. While we don't teach Aristotle's physics, maybe a little bit of Archimedes, but hardly any, thing before modern science in science textbooks. Of course, there's the reason I'm asking is that the present dispensation makes it a point that we should correct some of these historical notes which appear, because this, all Western names were not really the first to discover those theorems, etc. So maybe there's some justification for saying that Pythagoras theorem was also there in Baudhayana and so on. Now, do you see anything like that in science, or what you must have reflected on this? So is there something, because even in science we keep hearing that one in ancient Indian history you find scientific ideas and so on. So do these deserve to enter textbooks, school textbooks? What is your view on this?
No, actually I was very personally involved in it, in the higher secondary physics textbooks. And in the text writing. Of course, first of all, I entirely agree that textbooks should have historical orientation. History must inform science education, historical science. So that is one point. Because science education without, telling science without its history, in fact, is quite boring. History makes it very interesting. So that is one point. Now you are right, the whole problem is there are so many narratives, historical narratives. So for a textbook author, it needs a very important judgment, it needs quite complex judgment to be able to say just the right thing. I mean, what is the balanced thing one should say? So it's a very difficult problem, but still textbook authors should do that, and we in fact tried it. If you have seen, if you see NCERT books, I don't know the latest versions, but the laws of motion, which I myself wrote in the earlier NCERT text, I did start with Galileo experiment. I didn't start just Newton's laws of motion, etc. And we did talk about, I don't recall if we mentioned Aristotle, but sometimes we should mention some of these names in connection with the ideas which they had. They were brilliant thinkers, but their ideas have now been found to be, have now been replaced by such and such ideas. Historians of science, by the way, don't like such things, to make use of history, to gauge history from the present point of view. But for science educationists, I believe history has to be gauged from, because if you want to teach modern science, you have to see how it came along and what were the alternative ideas, without sounding disrespectful to them. You should not sound disrespectful, but you have to pick up the idea that led to modern science, etc. So I don't know what you are asking. I mean, yeah, I agree, historical narratives should inform, but the only thing is there should not be any specific purpose for that. The purpose should be good science education of students. If it is Indian authors, good science education of Indian students. That is all. They should be able to understand science and feel interested in science. Whatever it takes to use history to further this purpose, you should do this. So the learning of science should be the center of the goal, not some other goal. Other goals you satisfy in some other curricula on history or anything. But as far as science education books are concerned, their goal should be to use history to teach, to be able to learn science well. Okay, so now about the other narratives, the point that I said, the central point of my talk, I think it has to be driven home to many, many people, that science is not one concept. I don't know if you appreciate that, but when I thought about myself, I thought, well, it's something nice that has occurred to me, that not that it's an original idea, it's very well known, but I sort of appreciated it, that it's one particular concept, if has been talked about elsewhere, somewhere else, that's interesting, it's very interesting, but that doesn't show that the whole complex was there in that alternative thing. Science is not just one concept. Relativity is not that things are relative. Relativity means it's kinematics, dynamics, it's all its exploration. All that makes the relativity principle interesting. And if somebody has said all motion is relative in somewhere else, that doesn't mean, relativity was discovered at that time. However, all this has to be researched. If indeed it was the whole complex was discovered, then of course we have to give credit to that. For instance, in mathematics in India, there has been a series of great mathematical achievements. For example, in the Kerala school, which came quite close to infinite series and calculus and things like that. Of course, I think in any mathematics book this should be mentioned, because that is authentic knowledge, and it is quite a connected piece of knowledge that was established in some part of the world. So not ignoring in that and only saying Eurocentric things is also not correct. So we should not be anybody centric. It should be, science is nobody centric.
Yeah, thank you. I think concept versus theory maybe that captures the
concept versus the connection. I learned it from G. Nagarjuna. I don't know if he is there or not. He used to always say that concept doesn't have its meaning by itself. A concept derives its meaning from the web. It's a beautiful idea. And I think cognitive scientists, probably Sanjay would know much more about how it is. It's a beautiful idea. So I sort of in my thing I applied that idea to the exposition of modern science.
Okay, thank you. Any other questions? Okay, so there's, would you like to ask? Yes.
The role of history in science education. As a student, when I was a student in school and college, and when I was learning mathematics or science, the reason why the people or the scientists felt to discover something, for example, derivatives and that, what was the need? If that would have been explained in those times, in that perspective, I think that will make it interesting. Rather, who should get the credit of discovery?
What was the reason for derivative?
Why they felt that derivative should be involved? In what way?
You mean the differential coefficient?
So what was the need? What made them, why they were forced to discover that? What was the situation behind it? If that would have been explained, then it would become...
The issue was variable speed, you know, when a speed varies, then you should be able to define speed at every instant.
Okay.
So whenever the varying things are concerned, you have to, the notion of derivative comes up.
I think his question was, he was just saying that in textbooks we should emphasize on why there was a need for science to develop at any stage instead of focusing on who should get credit for the development.
Yeah, agreed. Who is not as important as the motivation for it. Why was that concept needed? Yeah, that's correct, certainly.
All right. If there are no questions, there is one related which you partially answered earlier, but aesthetic-like premise may have even may serve as a purpose how science or technology may look like 100 years down the line. So how, as a teacher or teacher educator, would you make the teachers to like emphasize this idea, or like when they hear something like stick to science, but this is equally important in class. So would you like to comment anything about how talking about premises is equally important, maybe when you are having a scientific discourse in class? Would you like to comment anything on that?
Talking about the premises?
Yeah. So any, so aesthetic is one example that was asked, but...
No, I think people, this point should be told to science students that science, the logic of science is the same logic as all of us. Science differs from its premises. That is one point. The aesthetic point was different, that the premises could be an aesthetic premise, but aesthetic, you can use aesthetics, but that is not justified per se. I mean, you can develop theories based on your aesthetic judgments, but that does not constitute its justification. And justification is only in its experimental verification.
Okay, so if there are no more questions, we have reached to the end segment of this session, which is vote of thanks. So thank you, Professor Arvind Kumar, for this insightful talk and about the nature of modern science. And I know there are many questions because it has given us a way or a direction how to connect nature of modern science, also with the premises and how would you take this connection to school and to all other educators and other community members in audience and outside. So I hope we will have more stimulating discussions outside on this. And so thank you again, first of all, Professor Arvind Kumar, for accepting VGK Memorial talk invitation. It is also, as Professor Bhattacharya already pointed out, it is our first event of HBCSE's Golden Jubilee celebration. So it's a double celebration for us today. I also take this opportunity to thank members of VGK's family who have showed the same love and affection towards the institute by actually being physically present here. Some of the VGK's friends and also Professor Arvind Kumar's friends, HBC alumni and other dignitaries are present in the audience today. So I would like to thank all of them and also those who are present online and were listening to the talk. Thank you all for your honorable presence. I thank Professor Arnab Bhattacharya and Professor Savita Ladage for this event. And there are a few people who are behind the scenes but have made this event successful. So I would like to acknowledge a few here. Thanks to Manoj Nair for creating the VGK Memorial poster. Thank you to the members of Center Director Office, Dean's Office and Public Relation Office of HBCSE, particularly Gajananji, Ravindra Sawant, Sumana Amin and Gaurav Girnar for your help in email communications, invitations and social media publicity. Thanks to HBCSC's technical support team for managing this event in hybrid mode. Thank you to canteen service, security and cosmetic staff for your effort to make this event more comfortable for all of us. And special thanks to Mr. Krishna Sahu, Head Finance and Services, HBCSE. Thanks to the audience, both in person and online. And I request now all to proceed for the high tea outside. And let's continue these discussions further. So thank you, everyone.